Hello everyone. In this video we're going to look at two practice problems to practice what we learned so far in Module 1 about random experiments, events, and simple probability calculations. So let's take a look at this one. This one says discs of polycarbonate plastics from a supplier are analyzed for scratch and shock resistance. The results from 100 discs are summarized here. And when we look at this table, we see that the summation of these numbers are 100. So basically we categorize these discs to high shock resistance, low shock resistance, high scratch resistance, and low scratch resistance. So we have these four categories. Then here we are defining a couple of events. So this is the entire sample space, basically. Let A denote the event that a disk has a high shock resistance, and let B denote the event that a disk has high scratch resistance. So high scratch resistance and high shock resistance define our events here. Determining the number of disks in A complement, A intersection B, and A union B. So here is a good point to pause the video and think about this practice problem and see what you can get for the number of disks in these events, basically. So hopefully you've had some successes with this problem, but let's now take a look at these events. A prime, A intersection B, and A union B. A prime or A complement is whatever it's outside of A. So what is A? A is high shock resistance. So high shock resistance is basically this column, right? This is A. 70 plus 16 is 86 disks have high shock resistance. Basically, they are in event A. Therefore, everything outside of that is in A prime. So you can say that this 9 plus 5 is basically A prime. So however you want to look at 100 minus 86 or 9 plus 5 is the number of disks in A complement. So I would say 9 plus 5 is basically 14 disks in A prime. A intersection B. B is high scratch resistance, so basically this is B. You can think of this little diagram that I draw here as a Venn diagram, basically. You have A and you have B in the entire sample space, and A intersection B is when a disk has high shock resistance and high scratch resistance, which is basically these 70 disks, right? High scratch, high shock. So 70 disks are in that area. And A union B, or also you can read it as A or B, is the union of these two events. Whatever disks that has high shock resistance or high scratch resistance is basically 70 plus 9 plus 16. There are only 5 disks that do not have either of high shock resistance or scratch resistance. So I would say basically 70 plus 9 plus 16, which is 95. You can get to this number by doing 100 minus 5 as well. So that was just a little practice to see the application of random experiments and events in quality control application. Later on in other courses you will see quality control, and this is a common application in quality control where you basically sample what you receive from suppliers and for their quality based on random sampling. So let's look at another example here. A random experiment can result in one of the outcomes A, B, C, D, So these are the outcomes with probabilities 0.1, 0.3, 0.5, and 0.1. And you can take a look here. The summation is equal to 1. So they form the entire sample space. We have all the 100% possibilities distributed between these four outcomes. Respectively, let A denote the event that contains these two outcomes, and B event BCD, and C is another event that only contains outcome D. It might be a little confusing here because we have A, but it's capital A, but here we have little a and b. But you have to be careful with this, and you differentiate between the outcomes that we have here and the events. This cap A, cap B, and cap C are events. So again, it's a good point here to pause and think about this problem with respect to what is asked here. These are probability of A, probability of B, and so forth. So you want to be able to calculate the probabilities of these events using the probabilities of outcomes. Let's start with the first one. This is probability of cap A, or event A, which contains outcome A and B. Outcome A has probability of 0.1. This is probability of 0.3. So because it contains both of those two, the event is the summation of these two. The event has both two outcomes. It's a good practice to draw a Venn diagram at this point. So here's the entire sample space, and we see that the outcome C, which is here, has a probability of 0.5. So I would say this is just little c, outcome C, and then outcome B has probability of 0.3, so let's allocate about 0.3 of the entire sample space to outcome B. And then we have A and D both 0.1. So 0.1 here and 0.1 here. So let's do this. Here is A and here is D. These are outcomes and they form the entire sample space. Now we're defining some events. So event A has the outcome A and B. So basically this is event A, right? So this is event A. Sorry for my bad drawing here. And that event contains those two outcomes. This outcome has a probability of 0.3. This one is 0.1. Therefore, we're adding those together. This is 0.4 is probability of event A. Now, what is probability of event B? Event B has outcomes B, C, and D. So I would say B, C, and D together is this one, right? Right, so this is the event, the black is the event B, right? And event B has outcome C, outcome B, and outcome D, and those are C is 0.5, B is 0.3, and D is 0.1, so that is 0.9. About 90% chance that event B occurs. Now, in event C, we only have outcome a little d, and that is 0.1. So probability of outcome D, which is 0.1. Probability of A complement. Now, A complement is, we know that probability of anything, any event complement is 1 minus the probability of the original event. So 1 minus probability of A. And we already know probability of A from this part. So this is going to be 1 minus 0.4. That is 0.6. Probability of A intersection B. Well, when you look at A, event A and event B, This is the outcomes in event A. These are the outcomes in event B. The intersection between these two is only B, right? Outcome B. So we just say it is probability of outcome B, that is 0.3. A union B is everything in A or B. So here we have A and B, here we have B, C, D. So together we have A, B, C, D, essentially everything. So that is 0.1 plus 0.3 plus 0.5 plus 0.1. That is 1. And that is the maximum probability that you can get, 100%. And A intersection C, we have intersection between A, event A, we have A and B in there, and event C, we have only outcome D in there. So there is no intersection, if you see here. I mean, there's no intersection, so probability is basically 0. So these are the two practice problems that we wanted to work on. There are more in homework and extra practice problems for this module, but this was just to warm up.